Okay, Atwood machine. This is a light frictionless pulley. Sort of frictionless pulley. Quotes around it because it's frictionless, but not really. Okay, then you got a mass M1 on one side, mass M2 on the other side. If these masses aren't equal, this thing's going to tend to accelerate in the direction of the greater mass, and that's obvious, right? That's our experience of the way things work. We intuitively know that when we're 3 years old. If I give a 3-year-old a pulley and put a big mass here and a little mass here, I think, I haven't tested this out with 3-year-olds, but I think he's going to tell me which direction it's going to go. Okay? And if a 3-year-old won't, a 4 or 5-year-old certainly will. Okay. Now, we did a trial where we manipulated weights. We had a washer here, and we had various numbers of paper clips and trying to balance the weight. On our very last trial, this mass over here descended 20 centimeters in about 4 seconds, starting at velocity 0. What can we conclude?
Acceleration is 5 centimeters per second squared.
Okay, could well be. Okay. Actually, I think the average velocity is 5 centimeters per second. Not alpha, this is A. Well, you conclude all this, and if you don't know how to conclude this, go back and review what we did Monday. Okay? Very simple. You could also use the equations of motion, but it's totally unnecessary when you have an initial velocity of 0 with this kind of information. You can get much quicker, you can pretty much do it in your head. Elam did this much in his head. That was initial velocity, right? Our average velocity. Okay? Okay, so, well, we got that. Okay? Now, let's digress to the whole thing, because this is actually a system with, you can model this system as an angular system, okay? Because you have this pulley, and the string is going over this pulley, and the string isn't slipping, right? So the whole system can be characterized by the motion of the pulley. Like, pulley has a diameter that we measured to be about 2.5 centimeters. Now that's the width of a domino, and we did this first in dominoes, right? You got to be able to do that. But the radius of this thing is 2.5 centimeters. If the thing goes 20 centimeters, well, that's 8 radii, isn't it? Okay, so I can say pulley diameter, or pulley radius, implies your change in angular position is 8 radians. Because 8 of these makes this. 8 times the radius is 20 centimeters, and you know this thing had to, a point on the rim had to move through 20 centimeters in order for this thing to drop 20 centimeters. Unless that string's slipping somehow, and it's not. Okay? That makes sense? And that's what a radian is. You got to get used to that. And by Monday, I hope you're totally used to this, okay? Get something out of the way that will be a big hang-up in about a month. And it won't be a big hang-up, so you'll understand the rest of what we're doing. You got to know this, and I want you to know it now. So average omega is 1.6 radians. Actually, this is 4 seconds, sorry, so it's 2 radians per second. And the angular acceleration is 4 radians per second divided by 4 seconds. And that would be, well, we're going to say 1 radian per second, but actually angles are measured counterclockwise from the positive x-axis. And if this is the mass that's descending, the thing rotated clockwise, didn't it? So that means actually we had -8 radians, and all of these quantities are negative. Okay? Okay. Now, we also, just did a quick estimate, running my finger over the top and hitting the pulley. We estimated the pulley was moving at a distance of 20 dominoes lengths per second, and it had a radius of half a domino length. And hopefully you wrote that down, and hopefully if you didn't write it down before, you just did, so you know what I'm talking about. Okay? Meaning that the distance that point on the rim moved, if it picked up the speed of my finger, which it probably did, was 40 radii per second. That's how fast my finger was moving. That's how fast a point on the rim was moving, which means 40 radians per second. That's what a radian really means. You can go to the definition, you get all the pi's and all the conversions into it, but that's what a radian is, and you got to get used to that. It's not a formula, it's an ideal. Okay, and you divide that by about the 20 seconds it looked like it took to come to rest, and you find that at least the average angular acceleration is about -2 radians per second squared, right? So one takeaway from this is adding these masses here and letting it accelerate. It accelerates more slowly than it does if you just use the bare pulley, okay? And that's because essentially you have more mass out here at the radius than you did before, more of the mass. Well, that's something we can talk about much later. But it's an interesting comparison. It's one you want to keep in mind, and you want to keep this calculation in mind just to help yourself get used to what a radian is. Okay?